Okay, ladies and gentlemen, so let's get started with today's class. Today, we're going to be talking about trigonometric ratios. And I know that if your geometry class, you guys saw or might have seen a little bit of trigonometric ratios. But what I'm going to do is I'm going to review the concepts based on what's in your textbook, and we'll do at least example one um, today in class. All right. So, one thing that we need to understand is that in its origin, trigonometry meant the study of triangles. And when in our previous class, when we talked about similar triangles, we said that similar triangles didn't necessarily need to have the same size in order for them to be similar, but that their sides were with each corresponding angle. So, for example, we had three or two arc marks here. We had a triangle with one arc mark here, and this side had three arc marks. And we would call this triangle A, B, and C. Right, let me see if I can draw the other arc mark right here. Let's see if I can draw it between these two. And there is our third arc mark. Okay, and we call this triangle A, B, and C. And we also had a smaller triangle that was similar to this one. Now, the orientation of these triangles were the same, but I was explaining in yesterday's class that I could very easily rotate or change the orientation, and I could still find corresponding sides based on where they were located in terms of their angles. So we have three. Let's see if I can draw the third one here. Three arc marks, and we had two arc marks here. And we had one arc mark here. And we'll call this D, E, and F. F. Let's see if I can fix that this arc mark here so it could look a little better. And see if I can draw one better here. And that way I can just kind of delete this one. And see if I can draw it now. So it looks a little better. So this one's supposed to have two arc marks. Let's see if I can fix it. One, and hopefully I can fix it here. And two. Yeah. Okay, so we said corresponding sides. So if I look at A is actually across the angle that has two arc marks. And if I look at my second triangle, so is D. So we say that there's a ratio of A to D. Now, we're going to talk a bit about ratios today, but not in the same way we did in our last class. But just to kind of review, A over D is a ratio because they're corresponding. If I look at C, it's across the angle that has one arc mark. So is E. So another ratio would be E to C, or C to E, excuse me, C to E, because they have corresponding sides. And if I look at B, B is across the angle that has two arc marks, just as is F. So we say B to F is another ratio. Now, if the triangles are similar, not only are they have corresponding sides like they do here, but the value of those ratios are actually going to be the same. And that's what we did in our previous class. And we also said that the angles would be congruent. So if for example, we'll call this angle here 1, we'll call this angle here 2, And we'll call this angle here 3. And this one will be 4, 5, and 6. So we would say that angle 1 is actually congruent to angle 4. And remember that this is the congruent sign. So angle 1 is congruent to angle 4. Angle 2 is congruent to angle 5. That means that they'll have the same measurement, whatever that measurement will be, is congruent to angle 5. And finally, angle 3, which is this one, is congruent to angle 6, which is down here, if I can find my marker. Angle 6 is congruent to angle 3. So we say angle 3 is congruent to angle 6. So two things that we could get from this that I've just reviewed. Number one is that corresponding sides are going to have the same ratio, and that corresponding angles are going to be congruent to one another. Okay, so that brings us to what we're going to be seeing today. And today we're going to be talking about trigonometric ratio. And basically there are 6 possible trigonometric ratios, and we're going to talk about that in a minute. Okay, there are 6 possible trigonometric ratios. Now, when we talk about trigonometric ratios, we're talking about a right triangle. That means a 90-degree triangle. It doesn't matter if it's 30, 60, 90, or 45, 45, 90. It doesn't matter how that is done. It's just as long as there's a right triangle. So trigonometric ratios are going to be done with right triangles, and usually we have a reference angle. Right now we'll call it angle Z or phi, which is the Greek letter. And it's usually represented with a little circle and the line in the middle, kind of like this. And we'll say, we'll label the sides of the triangle. Give me 1 minute here. Okay, we'll label the sides of the triangle as this side, the longer leg, we'll say is B. It's really irrelevant, but we'll say B. And what I mean by irrelevant is sometimes you'll have this leg called A and this leg called B, but here it says BA, and of course the hypotenuse is C. Now there is a ratio, just like there would be, other ratios. So for example, we can have the ratio of B to C. That's a ratio, B over C. And another ratio would be A over C. You would have, then you would have kind of like the opposites, and B over A, B over A. As I skipped that one. B over A. And the other ratios that you could possibly have in a trigonometric, in a right triangle, would be just to kind of invert them. So B over C, I could also say C over B. I could also say C over A. And I could also say A over B. So in a right triangle, I have 6 possible trigonometric ratios. And those ratios are just helping me measure the side length of the triangle. Okay. So again, the 6 possible, and we're going to go into that in just a minute, are B over C, A over C, B over A. Then you would have C over B, C over A, and finally A over B. Now, let's talk about that more specifically, because they're not just A over B or B over C. They do have names, and that's what we're going to talk about now. Okay. Now, before we talk about the names of the ratios, let's remember that we're going to be using our Z as a reference angle. So we're going to be using this right here as a reference angle. And based on this reference angles is the names that we're going to use for the trigonometric ratios. So for example, if this is my reference angle, one of the trigonometric functions that I use is called sine. And it's abbreviated with SIN, although it's spelled SINE. And sine is defined as opposite over hypotenuse. Opposite over hypotenuse. Okay. Hypotenuse. Opposite over hypotenuse. Now, what is opposite referring to and what is hypotenuse referring to? Okay, so this is what I mean. When I talk about opposite, I mean opposite of the Give me 1 second, guys. I'm sorry. Apparently today my internet is glitching. Okay, so when I mean opposite to the angle that we're going to use as a reference angle. In this case, we're using, and let me highlight it in a different color. In this case, the angle that we're using to as a reference is this one right here. Okay, so sine means opposite over hypotenuse, and it means the opposite angle or the opposite side to this angle. And opposite just means the farthest side. So the farthest side to this angle is B, and the hypotenuse is C. Okay, so in this case, C is always going to be the hypotenuse. In a right triangle, C is always the hypotenuse. Okay, so the ratio for this sine, in this case, is B over C. Opposite, because it's the farthest side from the angle, and C, because it's the hypotenuse. Next, we have cosine. Cosine is referred to as adjacent over hypotenuse. Now, adjacent just means the closest side to the angle. So if I look at my drawing, at my triangle, the one that I have here, which angle is closer to Z? Is it B or is it A? It's A. So A would be our adjacent, and of course C is our hypotenuse. So the reference for the cosine, which is abbreviated as COS, would be adjacent, which is A, over C, which is the hypotenuse. And we're going to talk about the tangent right now. Let me just move this over here so that way I have some more space on the board. So the tangent. So we have sine, we have cosine. Now we're going to talk about the tangent. So the tangent is defined as opposite over hypotenuse. So we have opposite and we have hypotenuse. or not over hypotenuse, excuse me, over adjacent. I'm thinking about something else. Opposite over adjacent. Opposite over adjacent. Now, opposite over adjacent, opposite to what and adjacent to what, right? Remember that we're using the Z, what I drew there and in blue, as our reference angles. There can be more than one reference angle, but for the time being, we're only going to use this one, okay? So opposite over adjacent means the opposite or the farthest angle, the farthest side from the angle, which is B. So we say tan equals, and let me see if I can, tan equals, or the ratio for the tan would be the opposite side of the reference angle, the farthest side, which is B, over the closest one, which is A, because A is closer to this angle. Now we've talked about the first three basic trigonometric functions, but we're going to talk about the so we're going to talk about the other six because they're so what you're going to do is so we're going to basically, we have sine, cosine, and tangent as the first three, and they're called, there's an acronym that's called Socatoa. Sine, opposite over adjacent, so. Cosine, adjacent over hypotenuse would be A. Let me fix that A. And tangent, which is opposite over adjacent, toa. Now we can also invert them, okay? And invert them basically means that if sine is opposite over adjacent, that means that if I invert that, I would get a different trigonometric function. In this case, that trigonometric function that I would get would be the cosecant. So I'm going to do it on this side. So cosecant is abbreviated as CSC, and it's the opposite or the inverse or the reciprocal of the sine. So if sine is opposite over hypotenuse, then the cosecant would be hypotenuse over opposite. So it's just, since they're ratios and they're technically, on the same triangle, I can invert them, okay? So hypotenuse over opposite would be my cosine. And if I look in terms of the ratios that I already have in my triangle, we can say that that it's the opposite of the sine. So if the ratio for sine was B over C, opposite over hypotenuse, so if the sine is opposite over hypotenuse and its ratio is B over C, that means that for the cosecant, which is the opposite of the sine, the ratio is C over B. Okay, so if sine was opposite over hypotenuse, the cosecant would be the hypotenuse over the opposite, which is C over B. Now, if I have the secant, we have the cosecant and we have the secant. The secant is the opposite of the cosine. So if the cosine is adjacent over hypotenuse, the secant should be hypotenuse over adjacent. Over adjacent. And we're going to see this in a minute with an example. And that way it'll be easier for you guys to visualize. Hypotenuse over adjacent. And this is that it takes me forever to write on this thing. Adjacent. And So if the ratio for the cosine was A over C, adjacent over hypotenuse, that means that the secant is, C over A. So we would write this as C over A. And lastly, we have the cotangent, which if you're by now, you should have deduced is the opposite of the tangent, because that's pretty much the last one, the only one that we're missing, right? So we'd say the cotangent, if the tangent is opposite over adjacent, the cotangent is adjacent over opposite. Adjacent over opposite. Over opposite. Adjacent over opposite. And tangent was opposite over adjacent, and cotangent is adjacent over opposite. So if the tangent was B over A, the cotangent is now A over B. And those are the 6 basic trigonometric ratios. There are the most common trigonometric ratio that you guys can use. Okay. And there are also other identities such as reciprocals. And we're going to talk about that in a minute. I actually want to see if we have an example that we can use. Okay, so I'm going to erase all this and then we'll talk real quick about the identities. I'm going to do example number 1 in your textbooks. And I'm actually going to go ahead and, you know what? I think I can just erase this. And I can leave the trigonometric ratios there so you guys can use them as reference. Let me see if I can erase the triangle. And although it shouldn't really affect it, but we'll do it in a different orientation just to have the same one that's in your book. So in example 1 in your textbooks, for section 1.3, which is trigonometric ratios, we have a triangle, a 90-degree triangle. Remember, you cannot use trigonometric ratios with triangles that are not right triangles. If they don't have a 90-degree angle, you cannot use trigonometric ratios. Now, let me change the color of the angle we're going to be using as reference. This is going to be our reference angle right here. And usually you'll see it expressed as the Greek letter Z or phi. And the measurement of one side of the triangle is 4 and 3. So we have 4. We have 3. And what we don't have is the hypotenuse. Okay? So let me erase some of these right here. At least these, because we don't need them right now. I am going to leave expressed, however, the definitions, so that way you guys, we have an idea of what we're working with, okay? So I know that sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent, the cosecant is the hypotenuse over the opposite, the secant is the hypotenuse over the adjacent, and the cotangent is the adjacent over the opposite. Let me fix this real quick because that does not look like an H. That does not look like an H. Let me just rewrite that. So this is hypotenuse. Hypotenuse over adjacent. Hypotenuse over the adjacent. I apologize for this, ladies and gentlemen. Okay, hypotenuse over the adjacent. All right, so in example number 1, the problem wants us to find the sine, the tangent, and the cosecant. So we're being asked to find, let me write it here. Find sine, tangent, and the cosecant. Sine, wow, let me change that color. I thought I had a different color. There you go. Find the sine, the tangent, and the cosecant. But what I don't have is the hypotenuse. So that means we're going to have to use the Pythagorean theorem that we did in the section 1.1, if I'm not mistaken. So to find the hypotenuse, we're going to say 4 squared plus 3 squared equals c squared. So because we need the hypotenuse in order to find the other ones. So 4 squared is 16. 3 squared is 9. And c squared is what I'm looking for. And we have 16 plus 9, which is what we're gonna add that, and then finding the square root of that will allow us to find the missing value. So 60 plus, and this is c squared, I'm sorry, c squared. 16 plus 9 is 25. And the square root of 25. And the square root of c squared, of course. And when I do the square root, it's going to say that c equals, because c squared, the square root of c squared is c, and the square root of 25 is 5. So that means that the hypotenuse equals 5. Now, the problem wants me to find the sine, the tangent, and the cosecant. So I actually have them here, and I know that sine is defined as opposite over hypotenuse. So let's look for the sine real quick. Sine is opposite over hypotenuse. Remember that the opposite refers to the opposite of the angle. So our angle is z, and the side that's farthest from z is 4. And of course, the hypotenuse, we found out that it was 5. So that would mean that the sine of z is 4 over 5 in this case. Now, we're going to do the same thing. Now, we're going to find the other thing that they want us to find, which is the tangent. Tangent is opposite over adjacent. Opposite to the z angle is 4, and adjacent to the z angle is 3. So we have that our tangent is actually 4 thirds or 4 over 3. You don't have to turn that into a decimal or anything like that. Just leave it expressed. And the last thing that we're being asked to find is the cosecant. Now, the cosecant is the opposite of the sine. So if sine is opposite over hypotenuse, and we determine that the sine was 4, which is the opposite, over 5, which was the hypotenuse, the cosecant is the opposite of the sine. So that means that our cosecant would be 5 over 4. So 5 over 4. And that is how we do example number 1, ladies and gentlemen. Example number 1 of your textbooks. Okay, we found the hypotenuse because it was missing. We found the sine, which was opposite over hypotenuse. We found the cosecant, which was the hypotenuse over the opposite, or 5 over 4. And we found the adjacent, or the tangent, which was in this case 4 thirds. Okay. Now, example number 2 says, for the given triangle, calculate the sine, the cosine, the tangent, and the secant. Now we're going to see that in a minute, but before we do that, I'm going to talk to you guys real quick about trigonometric identities. So that's one way of finding them. So I'm going to go ahead and clear the images, and next we're going to talk about or erase some of the images, and we're going to talk about the trigonometric identities. So I'm going to erase this real quick, because there's more than one way to find specifically the sine, the other three trigonometric ratios, which are the secant, the cosecant, and the cotangent. There are other ways besides the one that I just did in this exercise, and we're actually going to talk about those real quick. So I'm going to go ahead and leave this and erase this, and we're going to talk about the trigonometric identities, specifically for the cosecant, the secant, and the hypotenuse, and the cotangent. So we know that the cotangent, and let me label this right here as, right, see if I can bring them down. Actually, you know what? Let me erase this too. Okay, so let me bring that down. So this is what we're going to call right now trigonometric identities. There are many trigonometric identities, but specifically the trigonometric identities that we're going to talk about in this example are reciprocal trigonometric identities. Okay, so these are reciprocal. We're going to see more as we go further down to what we're doing, but we're going to see reciprocal trigonometric identities. Now I know that the cosecant is the opposite of the hypotenuse. Is the opposite of the sine. So I know that I can write cosecant as hypotenuse over opposite. But when I use a reciprocal trigonometric identity, I don't use this. I use a formula that we're going to talk about real quick. Okay, so we know that the cosecant is hypotenuse over the opposite. Now, what a reciprocal, when I flip a fraction upside down, it's called a reciprocal. So if I have 1/3 and I switch it over to 3/1, it's called a reciprocal. Well, the same is true with these ratios. So I know that I can flip over the sine and write it as hypotenuse over opposite, and that would be the cosecant. But another way or another identity is using this one, cosecant, and we're going to see this in the second example. Cosecant equals 1 over the sine. Okay, 1 over the sine. And it's 1 over the sine because it's basically telling me that I inverted the fraction. Okay, now if I look at the secant, I know that the secant is the opposite of the cosine, so I know that if cosine is adjacent over hypotenuse, the secant would be hypotenuse over adjacent. Hypotenuse over adjacent. Now, as a reciprocal trigonometric identity, the secant is basically 1 over the cosine. Let me write the z here. So 1 over the sine of z, I forgot to write that. And the secant is basically 1 over the cosine of z, because we know that the secant is the opposite or the reciprocal of the cosine. It's just that in some cases, you'll have the trigonometric identity, and you'll have to use the trigonometric identities instead of the way we did the first example, which we're actually going to see in a minute in the second one. And of course, the cotangent would be 1. We know that the tangent is opposite over adjacent. The cotangent, we said, was adjacent over opposite, and we used it in the previous example, but it also has a reciprocal trigonometric identity, which we're going to see in a minute. So we know that's adjacent over opposite. But if we use the reciprocal trigonometric identity for it, it would actually be 1 over the tangent of z. The tangent of z. The tangent of z. Let me erase that. The tangent of z. The tangent of z. Okay, so now we're going to look at that second example, but instead of using or finding the trigonometric ratios using the other method that we use, we're going to use the trigonometric identities. So example number 2, which is on page 30, if I'm not mistaken, of your textbook. 1 second, ladies and gentlemen. Example number 2 says, finding trigonometric functions values for a general angle if z is a right triangle. Okay, so in this one, let me erase some things here. Here you go. Let me erase this because we're going to use the trigonometric identities. Okay, so we're not going to use this part here. We're only going to use the and this was the secant. Let me write that because I erased it. The secant. Okay, and let's continue on. And I'm going to erase this. And I'm going to erase this triangle because the one that we have in this example is different. I'm going to do my best to write that. I just realized that I erased the cotangent. So the triangle that we have in example number 2, and again, I'm going to try my best to draw it, to replicate it. We have triangle kind of looks like this. And then there's like a 90-degree angle going straight down here. Let me make sure I write that 90-degree angle correctly. And we have the hypotenuse, which looks kind of like this. Okay, not bad. And this side measures 7. This side, the hypotenuse here. Remember, the hypotenuse is always opposite of the 90-degree angle, guys. The hypotenuse is always opposite the 90-degree angle. And it says that it's the square root of 65. Square root of 65. And we're actually missing this side, and we'll just label this side as x. In some books, they'll label that as either A or B, but just to avoid any confusion, we'll call it x. And the problem, example 2, wants us to find the cosine, tangent, and the secant. So just like in our other exercise, the first thing we need to do is find the missing value. So we use the Pythagorean theorem as well. And we know that again, and I forgot to write the reference angle. Let me use a different color for that one. The reference angle that we're going to be using is right here. Okay, so now we can use, so the first thing we need to do is find the value of the x, or the missing side of the triangle. So we're going to use Pythagorean again, and we're going to say x squared whatever x squared is, plus 7 squared equals the square root of 65 squared. So the square root of 65 squared. Okay, and the reason I'm putting the parentheses is because you'll see what's going to happen now. So x squared stays the same because there's absolutely nothing I can do with this. At least not yet. And I say x squared. 7 squared is actually the same thing as saying 7 times 7, so that's going to be 49. And what's going to happen with the square root of 65 as it's elevated to the power of 2, what's going to happen is, obviously, there's basically the square root of 65 times, it's going to be 65 times 65. But just to make it easier, what's going to happen is that since this radical is elevated to the power of 2, and remember that, and we're going to see that a little bit later on, but technically, whenever you have a square root, there's an imaginary 2 here. And this 2 is actually going to cancel with the 2 outside of the parentheses. And that's just going to leave me with 65. So that is actually 65. And now what you're going to do is just solve for x squared. So you're going to subtract 49. 49. And that equals 65 minus 49. And of course, x squared, I bring it down to my final answer, although it's not really my final answer. This cancels out here. And basically 65 minus 49 is 16. So I need to find the square root of 16 in order to get the value of the missing length. So this cancels out. So does this. And x equals 4. So I found the missing side of the triangle. X equals 4. So I know that this equals 4 right here. So let's see if I can write it a little bit. Let's see if I can write it like this. X equals 4. So now that I have the value of the x, I'm actually going to go ahead and erase the Pythagorean theorem process, and that way I have more space to work with what I want to do. If you missed it, you can always pause and rewind the video and go back to it and listen to the soothing sound of my voice explain it again. And we will then continue to or proceed now to answer the problem according to what's being asked of me. This is example number 2 of your textbook, section 1.3. Okay, so they want me to find the cosine, the tangent, and the secant. So the cosine is pretty simple because the cosine is just a number that is closest to the reference angle, which in this case is 4. So we'll say the cosine of z equals 4 over the square root of 65. Now, we need to rationalize our denominator, okay? So technically, if you leave it as 4 over the square root of 65, some people would agree that you're done. Others would agree that you have to have it expressed in its simplest form, which in that case means that you have to rationalize the denominator. But I'm going to basically follow this or do the same thing that your book did. And I'm just going to leave the answer expressed as the cosine of z being 4 over the square root of 65. So that's the cosine of z, 4 over the square root of 65. Again, you could rationalize it. Some people might. The next thing that I want to find is the tangent, which is the opposite over the adjacent. So opposite being the farthest side from the reference angle over the closest side to the reference angle. So the Tangent of z equals, the farthest side is 7, because that's the opposite. So you would say 7. And the adjacent is 4, so you would say 7 over 4 would be your tangent. Now, the last thing that I want us to find is the secant. So what we're going to do is we're going to use trigonometric ratios. So I'm actually going to go ahead and review that. So to find the cosine, it was adjacent over hypotenuse, which is basically 4, which is the adjacent to z, over the square root of 65. And the tangent, which is opposite over adjacent, is the farthest side from the angle, which in this case is 7, over the closest side to the angle, which is 4, and that's 7 over 4. Now I'm going to look for the secant, but I'm going to use trigonometric identity. So I'm actually going to go ahead and erase this and erase the extra information here that I don't need right now. And that way just be able to solve for the secant, which is the trigonometric identity that I want. And the secant is 1 over the 1 over the cosine. Now we know the cosine is, right, let me write that down again. We found out that the cosine was 4 over the square root of 65. That's the cosine. 4 over the square root of 65. But I want to use the trigonometric identity to find the secant, and the secant is 1 over the cosine. So the first thing I'm going to do is just substitute. So I'm going to say secant is going to be 1 over 4 divided by the square root of 65. And that really looks interesting. Some people might disagree that interesting is the best way to describe that because it just looks so scary. But remember that whenever you have a complex fraction like this, it just means that you're going to invert this. So the next step, and I'm actually going to write it in a different color so I can illustrate my point better. What I'm going to do now is invert this fraction. Okay, so basically write my denominator where my numerator is, and my numerator, bring it down to my denominator. So this would just be 4 over, or excuse me, not 4, I apologize. I inverted the fraction. So this would actually be whenever I'm going to work with a complex fraction, I'm going to invert the fraction. So instead of writing 4 over the square root of 65, that would actually be the square root of 65 over 4. Let me rewrite that 5. Square root of 65 square root of 65 over 4. And since I moved the 1 down here, that would be over 1. Although your book just skips that step altogether. And, with good reason, because it's pretty redundant. Because basically the square root of 65 over 4 divided by 1 is just the square root of 65 over 4. So our final answer is that the secant equals, or the secant of z equals the square root of 65 over 4. Over 4. Give me 1 sec, ladies and gentlemen. This is not cooperating with me today. Here we go. the square root of 65 over 4. And that is the secant of z, ladies and gentlemen. Pretty simple, nothing out of the ordinary. Now your LMS, the instructions for your LMS are already uploaded to College One, but just so you guys have an idea, basically you're just going to work on problems 1 through 6 that are on page 31. So let me just type it here as practice problems or problems 1 through 6, page 32. Okay, and that's it for this video, guys. Hopefully this was helpful, and I will see you in our next class. So bye-bye.